Okay, well, maybe we'll get started now. So it's a pleasure to have Hugo, who will give a second of his 3 lectures. Just as far as the rules of the road, if you have any questions, feel free to unmute yourself and just ask them. Alternatively, you can post them directly in the chat, but make sure to direct them to everyone so that we can all see and possibly respond. And if you're not using the microphone to ask a question, just mute yourself. Okay, well, Hugo, why don't you take it away?
Well, thank you very much. So can you hear me properly? Okay, perfect. So the goal of today's lecture is to do a brief recap on the better and that. Either you never saw it and it's going to be interesting to just have I mean, I'm not going to do the formula, but try to explain the program. So if you never saw it, it's going to be interesting. And if you already saw it, in any case, my goal is to try to highlight what really needs to be done carefully in this program. And after that, I will state the theorem that we will maybe prove 1 or 2 at the end of these lectures, but definitely deal with on Friday. Okay, so let me start with the transfer matrix formalism. So remember, our goal is to try to understand the large-scale behavior of the partition function or restricted partition function to certain 6-vertex configuration of the 6-vertex. So here and below, x will be just a vector x1, xn. N can be anything between 1 and n, I mean 0 and n, capital N. And we assume that 1 is smaller than x1, smaller than x2, etc., smaller than xn, smaller or equal to n. Okay? And we are going to consider the vector space omega, which is plus minus 1 to the n. I mean, sorry, omega, which is a span. Okay, omega span by the basis psi x for all possible x's as I defined above, where psi x is defined as follows. Psi x of I is going to be plus 1 if I is 1 of the xj, and minus 1 otherwise. Okay, so it's always an element of plus and minus 1 to the n. Okay, so basically the entry is plus 1 if you are in the set x1 to xn, and it's minus 1 if you are not. Okay, and the claim, which will be interesting for us and that I'm not going to prove, is that the partition function of our 6-vertex model is the trace of a certain matrix Vn, which is going to depend on ABC, to a power m, where Vn ABC is called the transfer matrix. And just to give you an idea of what this matrix can look like, if you look at Vn 1, 1, C, let's say I put A equal 1, B equal 1, and I pick an arbitrary C, this thing, when I look at psi x, so let's say I write it in the basis psi x, psi y, then it's going to be 2 if x equal y. It's going to be C, okay, let me maybe write something bigger. So it's 2 if x equal y. It's going to be C to the power the number of I such that psi x I is equal to psi y I if x and y are what we call interlace. So let me tell you just after what this is, and it's 0 otherwise. And interlace here, I mean, I am going a little bit fast because this formula for Vn is not going to be relevant for us. I just want to state it that you can try as an exercise to check the claim above. So this interlace means that x1 is small equal to y1, small equal to x2, etc., yn, or the opposite. So it's an interesting exercise to try to check that the partition function can be obtained as a trace of this matrix, and the special form of the matrix is irrelevant for us at this stage. So special form of the matrix of course, it's very relevant to be able to implement the better ansatz, but since I'm not going to give you the full formula, then it's not so important to know the form of the matrix. And by the way, it's a good exercise to try to prove the claim and try to find Vn A, B, C in general, because here I just stated it for A equal B equal 1 and C. Okay, that's perfect. Very good. Okay. So let me check. So I'm on page 9, now page 10. So the important second thing, actually, let me stay here. The claim 2. Oh, okay, no, I'm not going to have room to do it here. So the claim 2 is going to be the same representation for the n. So claim 2 is, if I look at this guy, where I restrict myself to configuration with n up arrows, I mean, I claim that this is equal to the following. So still Vn A, B, C to the power m, but here I'm going to add n. Let me emphasize it by putting something like that, where Vn like that is the matrix restricted to the vector space, which is spanned by the psi x with x equal n, meaning that x has n bits in it, x1 to xn. Okay, and the fact that Vn induces an endomorphism on this vector space is just due to arrow preservation, what we proved in the first class. Okay, so from these two claims, it becomes completely obvious that one wants to do is to study the spectral properties of these matrices. More precisely, what you would like to understand is what is the largest eigenvalue in absolute value. Okay? Why? Because this is what is going to give you the rate of growth, and this trace is just going to be related to this matrix. Okay? Okay, and that's exactly what the better ansatz is going to do. So better ansatz, it's the following kind of recipe for computing the largest eigenvalue of this V capital N N. Okay? So let me give you the program, how you implement, if you want, if you would be some kind of computer, how you implement the better ansatz in our case. So first thing you do is that you consider a family of half integers. I'm going to call them I index I, like that. Okay, you pick n integers, half integers, and just for simplicity, because you can always reorder, let's say that they are ordered. Okay, and maybe distinct as well. But anyway, you are going to see we are going to restrict ourselves to a special choice. Once you have given yourself these half integers, what you do is you try to find a solution lambda, which is going to be n-uplet. solving the following Bethe equations. So what are these Bethe equations? It's going to be you want that n over 2 pi times p of lambda I, where p is a certain function, minus 1 over 2 pi is a sum for j equal 1 to n of theta of lambda I minus lambda j. You want this to be equal to I for every I between 1 and n. Okay? So here you may wonder, okay, what is this p, this function p, and what is this function theta? Where they just, I mean, they are explicit functions. They are well-chosen functions, but they are explicit. And I don't want to give you the formula here because it's not going to help you in the understanding of the talk. So these are two functions, okay, explicit functions. Once you have done that, then you use a theorem, which is due, I guess, to Bethe. I mean, I'm not guessing, I'm saying, which says the following. It says that assume, so I'm assuming that just, I mean, don't worry, it's not a real assumption, but assume A is not equal to B, and this is more important, this I is I minus n plus 1 over 2, okay? So pick a special choice of the I. There are extensions to other choices, but for now, we are interested in this one. Then the theorem says that there exists an explicit vector. Let's call it, for instance, psi. Again, well, maybe that's not a good thing, but I mean, psi, which is a function of delta and a function of the choice of lambda that I found here. So if I have a lambda, I can create a psi such that this psi satisfies that Vn, when I apply it to psi, is equal to lambda capital N psi, where lambda capital N is given by a certain formula. So, okay, sorry. It's a function, by the way, of delta n lambda again. And it's given by the product, so it's a definition from the thing, j from 1 to n of L of e to the I pi of lambda j, p of lambda j, plus the same product with a certain function m, where, again, I need to tell you what L and M are, and these have the following fairly nice formulas. And M of z is a squared minus c squared minus abz over ab minus b squared z. Okay, so what is to be remembered in this theorem? What you need to remember is that if you give yourself this I, you end up with a certain vector, psi, and a certain lambda, such that Vn of psi is equal to lambda psi. Lambda is a real number, right? So this is suggesting very strongly, is a complex number, a priori, that lambda n capital N is an eigenvalue of Vn capital N. Okay, it's kind of a recipe that constructs for you eigenvectors and eigenvalues. Okay, let me just maybe copy this. Okay, so let's do like that. So we have this kind of recipe to construct what looks like an eigenvector. And by the way, just as a remark, if A is equal to B and N is even, then the theorem extends the same way. You get the same thing. So same result. And if A is equal to B and N is odd, in fact, there you need to adapt a little bit the formula, adapted formula for lambda capital N. Okay, you get another formula, a little bit more complicated, but you get still an explicit formula. Okay, so this was the third step of the Better on That program, which is to give this recipe to have what looks like an eigenvalue and an eigenvector. Then the fourth step is to remark that for delta equals 0, this psi has only strictly positive entries for every x. So it looks like for delta equals 0, psi is a Perron-Frobenius eigenvector of V capital N. By the way, V capital N is a symmetric positive function matrix. Okay, so it looks like it's a Perron-Frobenius eigenvector. Well, then just believe that it is the same for every delta. Okay, so maybe psi is always giving the Perron-Frobenius eigenvector, and therefore maybe lambda capital N is always giving you the Perron-Frobenius eigenvalue. So then, if I want to understand f capital N, well, this is going to be the limit, remember, as n tends to infinity of 1 over, oh, by the way, I put minus. Yes, delta equals 0 is the fermion case, indeed. Yes, exactly. So there you can compute things explicitly, and you can check by hand that it gives you the Perron-Frobenius eigenvector. Yeah. So f capital N, in the first class, I put a minus because I wanted to look at it as a free energy, but let's remove this minus. So let's say it's the limit of 1 over NL times the log of Z NM of N. Then here, if you think about it, you are going to get exactly the Perron-Frobenius, let me write it like that, lambda capital N Perron-Frobenius of ABC, which will be the Perron-Frobenius eigenvalue of lambda capital N, of V capital N of the matrix. This is very easy to check. You have a certain number of eigenvalues, and then when you take the trace of the powers of the function of the matrix, you end up only the largest one remain dominant. Okay, so it's very good because that means from the previous step that this is 1 over capital N times the log of Z of of the product of the sum of the two products that I wrote here. So what remains in this last step is to wish for the best and imagine that the lambda J condensate. So what does that mean? What do I mean by that? I mean that maybe 1 over capital N, the sum of the delta lambda J, converges when n tends to infinity, limit over m. You are entirely right. Sorry. Thank you. That this thing converges to a certain distribution, and then you can hope that the 1 over n times the log will have an asymptotic. Okay? Because it's kind of a Riemann sum against the lambda J. So if the measure of the lambda J converges to rho x dx, then the sum of something against the lambda J is going to converge towards the integral of this thing against rho x dx. Okay? So if the empirical measure converges, then I have a chance that this kind of Riemann sum converges. That's the kind of program. I went a little bit fast because anyway, I'm going to restate this thing more properly. So this is the program of the better ansatz. Pick the I, solve the better equation, plug the formula psi and lambda for the better roots, check that it's an Perron-Frobenius eigenvector or eigenvalue, and then try to prove that this lambda j, they are close in measure to a certain limiting measure rho, and just plug the formula for rho. So what do we need to be careful about when we do that? Well, there are several steps. There are 5 steps in this program. And basically, in each steps, we need to be careful. This is 12. So let's be careful about what we are doing. So first thing, well, step 1 is not raising any problem because, but you need only the highest eigenvalues. There should be some spectral gap, or you expect this to be given for. So even if you don't have a spectral gap, you have 2 to the n eigenvalues. So in the limit in 1 over m times the log, this only the largest one will survive. And in any case, it's really a true, it's a non-degenerate positive definite matrix. So it has only one, it has only an isolated eigenvalue, maximum eigenvalue. So in any case, you indeed have that. So what should we be careful about? So step 1, no problem. But already in step 2, I should maybe remind you that you need to solve this thing. Let's say here, let's even assume that we restrict ourselves to I minus n plus 1 over 2. Well, it's not completely clear that lambda 1, lambda n exists. Okay? Why should there be a solution to this thing? So we need to prove that. That's the first thing we need to prove. Why is there a solution? Now in step 4, so step 3, which was the better theorem, this is just algebraic. There is no problem there. You can justify it in very easy ways. There is no mystery there. But in step 4, when I'm saying that I'm expecting, in step 4, I was saying that I want this, this thing to happen. I want lambda n to always be the Perron-Frobenius eigenvalue. Well, let me even remind you that it's not clear that psi is non-zero. Because if psi, given by the better ansatz, happens to be identically 0, then it's not even clear that lambda capital N is an eigenvalue. Put aside the fact that it's a Perron-Frobenius eigenvalue, it's not even clear it's an eigenvalue at all. You need to prove that psi is non-zero. In step 4 again, it is not so difficult to prove this, that psi has entries of definite sign when delta is equal to 0. So for delta equals 0, for free fermion, it's easy to check that the entries are all of the same sign, either strictly positive or strictly negative, depending on how you normalize your vector. Okay, but is it true for other values of delta? Right, because this is at the core of trying to justify why lambda capital N would be a Perron-Frobenius eigenvalue. Okay? So that's another thing we need to check. And then in step 5, well, we need to prove condensation. So we need to prove that one of the capital sum of delta lambda I for I equal 1 to n converges as n tends to infinity, because otherwise we have a formula for x fix for each fix, n, but we want to take the limit when capital N tends to infinity. So we need to be able to have a formula which is tractable in terms of asymptotic expansion. Okay? So that's the 4 points that one needs to be careful about. And just to give you a little briefing on the historical, the bibliography, maybe let me call it like that. Well, the bibliography is really kind of strange in some sense, because if you run through the better ansatz, it's kind of clear that these are the 4 points that are a little bit tedious. But there is, it seems that every author is kind of proving that the better ansatz is rigorous, ignoring some of the steps. So they prove one of the things. And so, for instance, Yang and Yang, in a very famous paper, kind of justified existence. So in some sense, the step 2, and also something that I will come back to, that you can even find solutions that are continuous. Okay? So in some sense, for every delta, you can find a solution to the better ansatz equations, and you can even find it in such a way that it moves continuously with delta. So kind of very nice property. But they didn't deal with the condensation at all. That was a problem in this paper. This was an assumption. So in more recent papers, for instance, by Dorlas and Samsonov and by Karov-Kolzowski, condensation was proved, but under certain assumptions. So for Dorlas and Samsonov, it was for delta between 1 and 0, and n over capital N strictly smaller than 1/2 minus epsilon. So you stay away from capital N over 2. In Kozlovsky's paper, kind of addresses the most interesting case, which is the hardest one, and that's actually the one I will deal with on Friday, just to show you the hardest one, which is delta between -1 and 0. And again, under the assumption that small n over capital N is away from 1/2. There is something kind of critical happening at 1/2, and I hope that the proofs that I will present on Friday will kind of give you an idea of why this capital N over n, small n over capital N equal 1/2 is the hardest case. And by the way, let me tell you what these authors proved. What they proved is indeed that 1 over n sum of delta lambda I converges. It converges to a measure rho of x q dx, where, and here is, I need to tell you what rho of xq is, where rho of xq is the solution to what we call the continuous Bethe equation. Oh, sorry. Ah. Continuous Bethe equation. And this continuous Bethe equation is like that. It's for every x, rho of x q plus the integral between minus q and q of k of x minus y, rho of y q dy is equal to psi of x. And here I need to tell you 3 things, where k is p prime over 2 pi. K, sorry, not p, theta prime over 2 pi. Psi is p prime over 2 pi. So remember, p and theta are the guys involved in the Bethe equation here. These are these two guys. Okay? So you take the derivative, you divide by 2 pi. And I need to tell you one last thing is what is this q? So q is such that the integral between minus q and q of rho of x knowing q dx is is small n over capital N. So what do I mean by that? If you give me small n over small n and capital N, what they prove is that as long as you are kind of away, if small n over capital N is far away from 1/2, then 1 over n times the sum of the delta lambda I, so the empirical measure for the delta lambda I, the point measure, is very close to a continuous measure, rho xq dx, where rho xq is solving an equation. And there is some kind of normalization here that the mass, the total mass of my measure should be small n over capital N. Okay? So this is the result of Dorlas, Samsonov, and of Kozlowski. Okay. So my goal now is to give you our results on the Bethe ansatz, and you are going to see things are going to be a little bit more explicit and more quantitative than these historical things. So let's put 2 points. It's 2.2 results on Bethe ansatz. Again, maybe I remind you, so rho of xq is defined by solving this equation. And having this thing that the integral of minus q to q of rho of xq dx is equal to m. So, I mean, maybe I should, I should state it differently. Well, okay. So, rho of xq is solving this, and in this case, I write q equal q delta of m, sorry, okay? So for every m, I can try to solve this. I end up with a function rho xq, and this function, the q, is called q delta of m, okay? Okay, so first theorem, it's about the existence of condensed solutions to Bethe ansatz. And by this, I mean the following. If you fix delta, maybe fix it not equal to -1. I want to be safe in what I'm going to write. And fix n smaller than capital N over 2. Then there exists a lambda such that, oh, okay, so what do I have? I have that lambda is solution to the Bethe equations. So this will be the equivalent of the Yang and Yang paper. I ought to also have that lambda is symmetric. This is just because it's convenient. So it's lambda of n minus I equal minus lambda I, and ordered, meaning that lambda I plus 1 is strictly larger than lambda I for every I. This is just a tiny thing. I mean, this is not important. But the important thing is that it's going to be condensed in the following way, that for every function f from R to R with integrable derivative, then I have that 1 over capital N sum of the f of lambda I minus the integral between minus q and q of f of lambda rho of lambda knowing q, lambda q d lambda is smaller or equal to 2k over capital N times f prime, where q is q delta of small n over capital N. So it means solving this system of equations with m equal n over capital N. And k is equal to maybe let me actually not be explicit for now. Let's put a c of delta here. So you see, this theorem is saying not only you have existence of solutions, but these solutions you can find one which is condensed, which is already, you have kind of a very quantitative comparison between the sum over the f of lambda I and the integral. Okay, and this is as strong as you can hope for, basically, in general situation. Okay. So this for us was very nice and a very good surprise, because we have no assumption for delta equal 1. You need to be a little bit careful about this C of delta, but otherwise you have no assumption on small n. Okay. Any n smaller than capital N over 2 works, and as we saw before, the cases where small n larger than capital N over 2, since the model is arrow reversal symmetric, you can reverse all the arrows. Capital N, small n larger than capital N over 2 is mapped to small n smaller than capital N over 2. So this is the first result, and that will be one of the results we are going to prove on Friday. And you are going to see the proof is very simple, actually. So it's a little bit surprising that it was missed for so long. Okay, second thing, so this answers, by the way, it answers the existence step, and in some sense, also the convergence here. Okay? Now, we still need to handle the fact that psi is non-zero. And in order to do that, we are going to prove a second theorem, which is that not only you can find continuous solutions, but also analytic ones. So there are analytic families of solutions. And there, we are going to have to make an assumption. So if you fix delta 0, if you fix delta 0, let's say smaller than 1, I'm going to do it, let's say no, sorry. So there exists an analytic family of solutions. Delta gives lambda arrow of delta. By analytic, I mean that every entry is analytic. In the following cases, so the one that is going to be very interesting for us is if 0 is smaller than delta, smaller than 1, and small n smaller than capital N over 2. So you can always create an analytic family in this direction. And in fact, this is a very easy thing to check, and I will show you how. You can also do it, and this is the most interesting case, if you take -1 plus epsilon, smaller than delta, smaller or equal to 0, and small n smaller than capital N over 2 minus k of epsilon, and n large enough. So this is important, and I'm going to tell you why in a second. And then for delta smaller than -1 minus epsilon, and n smaller than capital N over 2, and n large enough. So what does it mean? If I draw a picture, when can I construct an analytic family? So there is 1, 0, minus 1. So for any small n smaller than capital N over 2, I can construct an analytic family on this whole thing. There is no problem. Okay? If I take n smaller or equal to capital N over 2, and I fix myself a place close to minus 1, on this whole thing, I can do it as long as n is large enough. So it's not true that for any fixed n, I can go up to minus 1, but it's true that whatever delta smaller than minus 1, I can go up to this delta as long as capital N is large enough. Okay? And the last and more important case is if I fix a delta larger than minus 1, I can create here, as long as small n is smaller than capital N over 2 minus a certain k. So if this is epsilon, it's a k of epsilon. And also, I want n large enough. So here, in some sense, we are using an assumption. We cannot, I mean, we don't manage. What we would like very much is to get this without this guy. We would like to be able to construct for any small n smaller or equal to capital N over 2. We don't manage, but it's going to be sufficient for all applications, and it's still much better than the known result that were for really small n smaller than 1 minus epsilon times n over 2. So where you really needed to be macroscopically away from capital N over 2. Okay? So why is this thing important? Because it's going to give us the last theorem, which is the Perron-Frobenius eigenvalues, and which is saying that for small n, capital N, delta in the previous cases, lambda capital N n of ABC. So delta here is delta of ABC. Huh? So I remind you it's c squared minus a squared minus b squared over 2ab. Oh, no, sorry, with the notation I took for this class, it's the opposite. So this is the Perron-Frobenius eigenvalue. So this is the last step, the last thing we needed to justify, to fully justify the better ansatz. Right? Okay. So just to notice that these things kind of work well together is that these results, they imply the following. They imply that f capital N n of ABC, remember this is the limit, I mean, it was 1 over n times the log of the lambda Perron-Frobenius of ABC. But because of theorem 9, 8, and 7 together, this is also like the integral between minus q and q of, so let's go back to the how this thing looks. So here we see a product of L of e to the IP. So if I define, I mean, here I'm going to get log of L of e to the I p of x, rho of x knowing q dx. And the error we are making is going to be of order 1 over n, because that's the error we are making here. So all these theorems together, they give you an approximation, a very good approximation for f capital N n. Okay? By the way, I can already tell you kind of the proof of theorem 1. which was the computation of the free energy. So remember that Z capital N, Z is the sum over N of Z capital N, N. So this implies automatically that F capital N, which would be, let me write it like that. This implies that F capital N, which I would define like that, sorry. The limit when M tends to infinity of 1 over Nm log of Znm. Then this, it's easy to check that it's the max over N of the Fnn. Okay? It's kind of the same as the comment of Reda, that there is, here you have a finite number of these. So the rate of growth of the sum is the rate of growth, the maximal rate of growth of one of these guys. Okay? But this guy, it's very easy. It's a good exercise to check that it's F capital N over 2. And this goes back to the question of Rick, which is that if you don't take A1 equal A2, B1 equal B2, C1 equal C2, it may not be capital N over 2, but we are in the symmetric case, so it is capital N over 2. And this, by the formula we just derived here, is the integral between minus Q of 1/2, Q of 1/2 of log of L of e to the I P of x, rho of x knowing Q of 1/2 dx. And here you have to trust me, but it's easy to check, that Q out of 1/2 is minus infinity. Q of 1/2 is plus infinity, sorry. So in this case, when you are trying to solve here this equation, but you put here Q equal infinity, you end up with an equation which is very simple to solve in Fourier. So you end up with a rho here, which is quite explicit. So this rho of x is 1 over 2 zeta cosh of pi x over zeta. Okay? It's just by solving directly the continuous Bethe equation, when Q is equal to 1/2, it's trivial to solve. When, N over capital N is equal to 1/2, Q is equal to infinity, and it's trivial to solve. Okay? So in this case, this L was very explicit. Remember that this was given by this thing. Okay, maybe it was, maybe M could also be mattering here. I should have told you that here L is mattering since A is larger than B. So when A is larger than B, the L is giving a bigger contribution than M. This is just a detail. But here L is explicit, rho is explicit, and in fact, if you go to Fourier, so you just transform in Fourier, you end up with a formula for f of ABC. Okay, this is this plus big O of 1 over n. So when n goes to infinity, you end up with the integral, and the integral you can compute by Fourier. So this is a very brief, but somehow I guarantee that if you are ready to do the computation, there is not much to be done to really fully get get a full proof of the theorem once you have this kind of explicit formula. This is really the core, and this formula, you have it automatically once you have the 3 theorems. Okay? I still have 20 minutes or something like that. So what I would like to do in this last 20 minutes is to tell you a little bit about why we focus on analyticity and not continuity. So let me tell you why I'm talking about that. and why we do that. Okay, so in the original paper of Yang and Yang, and even in more recent results, people were working to justify the existence of a continuous family of solutions. By the way, if you apply the ideas that we are going to develop on Friday to prove this theorem 7 of existence of condensed solutions, if you apply these ideas, you can see that the Yang and Yang argument, or other arguments in the literature to prove existence of continuous families, you can assume are in fact condensed. So it's kind of very nice. You have a condensed family. By condensed, now I really mean this property here. This is what I call condense, okay? So historically, you can prove existence of continuous families of solutions. I'm claiming that if you apply the same reasoning with the twist, with the idea that we got to prove theorem 7, you get condensed. So in some sense, it looks like you get everything what physicists were looking for. There were people looking for continuous solution and people that were working hard to prove that you have condensed solutions. Okay, so here you get both at the same time. But what is unclear to me, and I really couldn't make sense of this, is that I couldn't see why continuity helps you in any way. Doesn't continuity imply continuity of the entries of the parent? Yes, indeed. Like, yes. Yes. So indeed, you want continuity to, people were proving continuity to prove that your parent-Frobenius eigenvector varies continuously. Yes, Rick, you want to say something, it seems.
Yeah, if you have, you know that when delta equals 0, the entries are positive.
Yes.
They're continuous, then they remain positive for nearby.
Yes.
You get the parent-Frobenius eigenvector nearby. For nearby.
Yes, that's true. Yeah. That's going to be at the base of what we are going to do in the next slide. Yes. But what do you do after that?
Well, you just continue. You just continue to change delta. Then values can never become negative because you're always at the parent-Frobenius eigenvector.
No, but the problem is that psi can become 0, and if psi becomes 0, it's a barrier you cannot pass just by continuity.
No, that psi is, the entries are positive. You can always rescale so that it remains positive.
No, if you rescale, then you are going to see. Proving analyticity actually requires to prove something which we don't know how to fully justify, and this thing is exactly the norm. It's exactly related to the norm of the the eigenvector given by the beta ansatz. So it's at the end, it's an equivalent question in some sense to prove that psi is non-zero, or to prove that that you have analyticity. Okay. So I really don't. We can discuss this more if you want after, but.
Okay. Thanks.
Would you need uniformity in N for a continuity argument? You see, the problem is that. What do you mean by uniform continuity in N would not really solve your problem. So I completely agree. It's going to be part of the argument. Maybe, okay, what I suggest is I just present the next slide, like that I finish the lecture and we discuss this, because I would be very interested in an alternative way of doing, because we looked for that for some time, but we are not really specialists. So, who knows if there is not a simple way to get around it. So let me first finish and then we discuss all of that, because you will have the argument in mind and it will be simpler to discuss. So let me prove theorem 9 in the way I managed to prove. So theorem 9 is to try to justify the fact that it's a parent-Frobenius eigenvector. Okay? Okay, so we need to prove, so let's assume we have a family of an analytic family of solution to the Bethe equation. And let's say that psi of delta and lambda of delta are respectively the vector that the Bethe ansatz spits to you, which is psi of delta, and lambda of delta is a solution, is the eigenvector. Psi here should be ABC, by the way. Well, okay. Let me first fix A equal B equal 1 and C equals square root of 2 minus 2 delta, which is one example of choices of ABC that gives you delta as a spectral parameter. And let's assume you have this thing, which is analytic. And lambda of delta and psi of delta are the eigenvector, the vector and the potential eigenvalue given by Bethe ansatz. Okay? So from that, first thing, if delta equals 0, then there you check very easily that psi of 0 has strictly positive entries. And therefore, lambda of 0 is lambda Perron-Frobenius of 0, where lambda Perron-Frobenius of delta, so here lambda Perron-Frobenius of delta is a Perron-Frobenius eigenvalue of Vn capital N, of delta, okay? Okay, so at 0, everything is fine. And since the entries are strictly positive, you're entirely right, Rick. Psi of delta is the Perron-Frobenius of Vn. Let me drop the dependency in N because it's not relevant here, of V of delta for small delta. So this is perfect because that tells me that lambda of delta is equal to lambda Perron-Frobenius of delta for small delta. Right? This is what it gives you. So you start from 0, you have strictly positive entries. That means they stay strictly positive for delta close to 0. By the way, I treated the delta equals 0 case. Let me mention later the delta, when delta is smaller than -1. But, so you get strictly positive entries near 0. Therefore, you are the Perron-Frobenius eigenvector. Therefore, lambda of delta is lambda Perron-Frobenius of delta. But now, everything is analytic. So if everything is analytic, that implies, so this was by analyticity, this implies that lambda of delta is lambda Perron-Frobenius of delta for every delta in your set that says that it's analytic on minus uv. So in minus uv. Okay, u and v are positive numbers, as long as included in -1, 1. I want to include in -1, 1 because at -1, the functions themselves don't vary analytically. The p, the theta, the L, all of that. So, L actually does, but the others do not. Okay, so let's stay there. Everything varies analytically because lambda of delta varies analytically. Okay, but if this is the case, I can combine this with another observation, is that psi of delta is also analytic. So psi of delta is non-zero because it's non-zero at 0 for all, but finitely many deltas. Okay? So psi of delta is non-zero, but when psi of delta is non-zero, then it is really an eigenvector for lambda of delta. But we just proved that lambda of delta is giving you the Perron-Frobenius eigenvector. So since psi, if psi of delta is non-zero, then psi of delta has definite sign entries. By the way, actually, this was what we wanted to prove. Huh? This is what we wanted to prove for these weights, for weights A, B equal 1 and C equals square root of 2 minus 2 delta. But if I want to go a little bit farther, so if psi of delta is non-zero, then psi of delta has definite sign entries, and therefore, whatever A, B, and C, such that A squared plus B squared minus C squared over 2AB is equal to delta, psi of delta is the Perron-Frobenius eigenvector of the matrix VABC. So this, in addition, tells you that lambda Perron-Frobenius of ABC, now not just of this weight A equal B equal 1 and delta given by, C given by square root of 2 minus delta. Whatever the weight ABC, the Perron-Frobenius is going to be given by the beta ansatz. Okay, so it goes in 3 steps. At 0, it's Perron-Frobenius, so nearby it, the entries are strictly positive, so the eigenvector must be, the eigenvalue must be the Perron-Frobenius eigenvalue. By analyticity, this goes up to the whole interval, okay? That means that actually psi has strictly positive entries. I would like to say everywhere, I cannot prove that. I cannot prove that the beta ansatz doesn't give you 0 eigenvector for some values of I. I definitely don't believe it's the case, but I cannot prove it. So that means that psi of delta, at least for all but finitely many cases, gives you a non-zero eigenvector. And that non-zero eigenvector guarantees that whatever the other choices of ABC, you end up with the Perron-Frobenius eigenvalue. That's the end of the proof. I mean, actually, you could even have, if you are only interested in A, B equal 1, you can even close the deal here. So now, what I cannot rule out is that, I mean, of course, I don't believe it's the case, but I mean, even asking Carol and people who know fairly well, I don't know how to prove that psi of delta doesn't do a strange thing. If you don't have analyticity, you can imagine that psi of delta has strictly positive entries and kind of decrease in a norm up to a point where it ceases to be positive, strictly positive, it gets to 0. And then it could remain equal to 0. I mean, this is completely absurd, but I don't know how to rule out this behavior. If anybody has a rigorous proof that this cannot happen, this would be very nice because, I mean, it would not change the strength of the theorem, but it would kind of simplify this condition on capital N and things like that, on small n regarding to capital N. Obviously, I mean, I would be the first person to tell you there is absolutely no chance that the Perron-Frobenius the eigenvector is getting to 0 and remaining at 0. I mean, but the formula given by the beta ansatz is a nasty formula. So checking that this psi of delta is non-zero is not straightforward. At least I don't see a trivial way of checking it for every delta. And rescaling it is not going to be solving your problem because it's, I mean, the renormalization is not important in some sense. It's not, if you renormalize it, then you have the risk of reaching a delta where indeed you get a limiting vector, but then it's not given at this delta by the solution of the, by the lambda. Okay, that's all for today. So on Friday, I will tell you about the existence. So theorem 7, and I will tell you about theorem 8. And in theorem 8, you are going to see that we are going to want to compute something. And this something actually is exactly related to the norm of the Bethe vector. So yeah, I want to prove it's non-zero. Well, you are going to see exactly the form and what you need to prove. And then I'm not saying that with additional work it's doable. It's not doable. That I agree, Rick. But the Perron-Frobenius eigenvector can just rescale more and more to zero. I mean, the eigenvector given by the Bethe ansatz can just rescale to zero.
Yeah, but it's a projective object, so you can always rescale. So
if you rescale it, then you don't know that at the limiting delta, it's going to be given by the delta, by the formula that you get from the Bethe ansatz. Yes, you can rescale it, but then it's just, I mean, just think that at a given delta, the formula from the Bethe ansatz can give you zero, okay? So then for all the delta smaller than that, you can rescale as you want. Indeed, you can just rescale for it to be of norm 1, but then you don't have continuity anymore if you rescale in such a way that if you rescale by a norm which actually is going to zero more and more.
Okay.
So I mean, you can, what you are saying, which is entirely right, is that if you rescale properly, you can construct a Perron-Frobenius eigenvector for the limiting guy. That is completely true. And by the way, continuity would also give you that the limit of the lambda n for the delta smaller is giving you the Perron-Frobenius. But what is unclear is that this guy would be the guy given by the delta, I mean the lambda at this delta. And if you don't have this property, you cannot go farther. If you have this property, that it is giving you the psi of delta is indeed the guy that you would, so you take your rescale, you get a psi tilde of delta. If this psi tilde of delta is related to the psi of delta that you get directly, then that means your psi of delta has strictly positive entries and you can keep going. That I completely agree. But if you rescale the psi of delta prime for delta prime smaller than delta, you have no guarantee that in the limit, you are going to, and the limit is going to be related to the psi of delta that you construct from Bethe ansatz. I mean, there may be a way around it, which is cleverer than what I can come up with. I mean, I came as an outsider, so I came with my small hands, right? I mean, trying to, Trump style, small hands. I just tried the small things, but we couldn't come up with an argument involving only continuity, but there may be one.
Okay.
Well, let's thank Hugo for his lecture.
Thank you.
And as long as he promises not to compare himself to Trump anymore, we can ask questions in addition to what's already been asked.
So are there other questions? I mean, I know that I went a little bit fast maybe on certain steps, so don't hesitate to ask questions. It's not a style that usually I can only hand wave arguments, and here it's closer to the arguments that you can fully present, and it's very dangerous because you think you can fully present them and then you realize in the middle that there are all these tiny details that you cannot present. So.
I think it was very good though. Okay, so if there are no further questions, we certainly had active discussion during the talk. So what we'll do is the next talk, which is given by Rick, will start in 20 minutes. And I'm going to close out this session so we don't end up with any phantom sessions like we have in the past. And then I'll immediately restart it. And those who want to join immediately can do so, or you can wait and join in 20 minutes. So let's thank Hugo again.
Thank you.
His third lecture will occur on Friday, 11 a.m. Eastern Daylight Time, whatever that happens to be in your time. Okay, so we'll see you in a little.
Thank you very much.